So in this video lecture, we are going to be talking about Newton's laws of motion, and this will just be a basic introduction. So you may have heard of Newton's laws of motion. I'm going to just introduce them here and give some basic descriptions because we're going to be using Newton's laws of motion as we go and develop this computer code and eventually our simulation. So here we are in the video series. We're on video 1. What are Newton's laws of motion? So here they are. Newton's first law is also known as the law of inertia, and it says that if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed unless it is acted upon by a force. So basically, a body in motion is going to stay in motion, or a body at rest is going to stay at rest unless you change something dealing with the forces that are happening. So if we are... Let's just talk about this. If we are sitting in a car, you're going to be amazed by my awesome drawing skills. Okay, there's a little truck, I guess. So if our truck is just sitting there on the road, it's just going to sit there. It won't do anything unless we put a net force on it. So we could start the engine, push on the accelerator. That's going to create a forward force, a net force. The wheels will start turning and our truck will accelerate. Once the truck is going, and if it's going along at a steady speed, all the forces again become balanced, and it'll keep going along at that steady speed unless something changes with the forces acted upon it. So if we're cruising along at a steady speed, if we want to slow down and we apply the brakes, well, now we have changed the force. That'll cause our car to decelerate, which is another way of saying negative acceleration. So that's Newton's first law. Something is just going to keep doing what it's doing unless you make some kind of change to the forces on it. Let's go on to Newton's second law. This one comes with an equation which is very useful, which is F equals m times a. So what does that mean? F is the force, m means mass, and a means acceleration. And this says the time rate of change of the momentum of a body is equal in both magnitude and direction to the force imposed upon it. So let's think of an example for how we could apply Newton's second law of motion. So let's say we have a force. Let's say it's a big, strong guy with these big muscles, and he is going to be pushing our little truck, which looks just amazing. So he is pushing that truck. So if we assume that the force that he is applying is constant, and if he's pushing a big truck, yeah, he might be strong enough, if the brakes are not on, he might be strong enough to cause that force. Again, with Newton's first law, he might be able to change the velocity of that truck by applying a big enough force to it. Let's say we take that same guy, still a very tough guy with these big muscles, and now let's say he's pushing a much smaller truck. So if he's getting the big truck to accelerate, he's probably going to be able to get this smaller truck to accelerate even more by applying that same force. So if we apply Newton's second law of motion, force equals mass times acceleration. If the force is the same, well, this product, mass times acceleration, that has to be the same as well. So in the first case, let's call this F1, M1, and A1. And in the second case, we have the same force. Let's keep that as F1. But now if we have M2 and A2, if we wanted to figure out how fast that truck is accelerating based on the force this guy is putting on it, we could solve for A in both cases. And here we'd get A1 is equal to F1 divided by M1, and we would get A2 is equal to F1 because it's the same force divided by M2. So in this case, if this is our mass 1 and this is our mass 2, we can clearly prove mathematically using Newton's second law that we would expect the acceleration to be much higher in this case with the smaller vehicle because we're taking that same force, but we're dividing that by a much bigger mass. So it should be fairly intuitive, and the concept should make sense. But Newton's second law gives us this nice mathematical equation that we can use. And we're going to refer back to Newton's second law when we get into this conversation of actually simulating what might happen using these laws of physics. All right, so Newton's third law, action and reaction. When two bodies interact, they apply forces to one another that are equal in magnitude and opposite in direction. So let's go back to our guy pushing the truck example. Here's our guy. Here's the truck. Just gets better every time. So this law really applies best when you have a steady situation. So let's say this guy pushes this truck. He causes it to accelerate, and he gets to the point where he's pushing it along at a steady speed. So really what's happening there is he's pushing it along at a steady speed, but this still isn't easy. Even though he's got the momentum going and the truck's moving along at a steady speed, it still takes some strength. So why is that? Well, that's because the truck is pushing back on him, and really this is going to be a friction. The truck is heavy, it's weighing down on the ground, so there's friction in the wheels dragging on the ground, and then those wheels turning itself. So when he's pushing this along at a steady velocity or at a steady speed, the reaction is equal to his action, so that those forces would be equal on each other. However, the way that Newton's law is usually worded, there's some qualifying language in there that is kind of missing. It's saying they apply forces that are equal to one another, that are equal in magnitude and opposite in direction. So when the car is actually accelerating, this statement is not quite true. But basically, the difference there is the acceleration itself. So if the truck is going from a stopped position and he's accelerating up to some kind of steady speed, let's call it 10 miles an hour, he's kind of running as he's doing this. Really, it's the force that he's applying is equal to the resistance force plus that ma force, which is the acceleration term. So when you apply a net force to something, you're actually causing it to accelerate. So Newton's third law is really useful. We just have to remember that if there's a net force in one direction, then that body is going to be accelerating in that direction.